When we speak about software, at least in polite company, we tend to do so in positive terms. We speak of what the software will do, the problems it will solve, the ways in which it will make our lives easier. But the world is nowhere near that simple, is it? There's a duality to reality, and so for everything our software does, there's something it doesn't do. For every problem it solves, it creates still others, and if it makes our lives easier in other ways, it will make them more difficult. And this duality, this positive bias, is embedded in what I believe to be an archetypal story, something I've seen happen to other people and something that has happened to me myself. It goes something like this. A team of software engineers spend weeks or months building a software artifact, unit, and integration testing it. And then, finally, it's time for functional testing. It's time for a mock deployment. And so they start their program. It sinks into the darkness of the terminal, and in the background, it races on, doing thousands or millions of operations it was carefully programmed to do. And after some amount of time, out of the darkness of that terminal comes some output. The engineers doing the functional test see it. Error. No such file or directory. They look on in horror. Only milliseconds before, all of the precious context needed to diagnose this failure was resident in the program's memory. But now it's gone, leaving only this mocking error message. And then I come along to add insult to injury. I come along to say, this actually isn't even that bad when we consider the alternatives. Because that program at least recognized there was a failure. It didn't just careen on, leaving the mistake to be discovered hours or weeks or months later. And it made some effort to tell us what went wrong. It at least gave us something more than just error and a termination. And when terminating, it didn't dump core, it didn't get a segmentation violation, and it didn't hang for 12 hours only for some hapless system administrator to wander by and see no output in the logs and investigate further. No, this example is actually better than a lot of production programs. It's better than a lot of production programs that I know of running in production today. And this should give us pause, should give us occasion for reflection. We should step back and say, maybe we can do a bit better. So let's talk about the high-level thing that happened when we encountered the failure. The program ended. And there's nothing wrong with that. Programs aren't humans. They don't think in fuzzy terms. They can't go off and divine how an environment should be adjusted so they can perform their high-level task. They don't even really know their high-level task. They just know some finite set of operations. No, there's no problem with terminating, but how do you get there? Do you call something like abort or exit or terminate? Or do you carefully structure your application from the lowest level to the highest level to transmit that error context, and then only at the highest level do you make the final decision to end the program? And I would posit that that latter approach is much, much better. I would posit that exit and abort and terminate are equivalent to things like goto and global variables, that they should be prescribed for the same reasons. The reason we don't like goto is because it introduces non-local control flow. You can no longer look at a small section of code and determine all the ways in which control can pass through. It expands the amount of context you need to keep in your mind to reason about that code, and therefore increases the odds you'll make a mistake. And using exit or terminate or abort does exactly this. If I look at a function signature, how can I tell that control can not just flow out through the return path or through an exception, but can also just suddenly end my entire program? Global variables, on the other hand, we don't like because they have non-local effects. We can look at a function signature that doesn't use globals, and we can reason about the possible set of effects it could have by way of its parameters. If, however, we introduce global variables to the mix, it could go off and it could mess with state in any one of a number of different ways. Our ability to reason about the code is destroyed. But exit and abort and terminate don't just reach out and touch 2 or 3 or 4 global variables. They reach out and they destroy every single global variable. They destroy every single local variable. There is no piece of your program state they don't destructively touch. In some sense, a single call to abort or exit or terminate destroys the entire conception your program has of the whole universe because the process apartment rapidly collapses. And the alternative to this is something that software engineers should love. Being archetypally lazy as we are, we just kick the can down the road. When we're writing a very narrowly defined software component, we don't have information about how our user wants to handle errors at the highest level. We don't know the proper high-level action to take, and so we just don't make any decision. We kick the can down the road, we gather up the necessary context, and we make sure the next person up the chain can make the decision in turn. Distilled to a fundamental principle, we don't make assumptions about what our user wants that are outside the well-defined responsibility of the component that we're writing. We defer those decisions and we let someone make them later. Now that we have this principle, let's think about that error message. No such file or directory. And this isn't that bad of an error message if all you know is enoent. It's a pretty standard error message for enoent. No, the problem with this error message isn't what's in the string, it's what's not in the string. And when we think about enoent, we think about the occasions in which we see that error code, we think there must have been a call to syscall open. It returned -1, it set erno, and the application recognized this error situation. It grabbed erno's value of enoent and it propagated that, but we know that a call to open includes a path. It includes the vital piece of context that could have helped us sort out what went wrong in that first example. But that component made an assumption on behalf of its users. It expanded its responsibility and decided that there was no circumstance in which its caller actually needed that context. And so it dropped it on the floor and doomed us to the situation we now find ourselves in. So armed with this principle, let's talk about integer parsing. Let's talk about all the ways the standard library gives us to parse integers, and let's examine why exactly they fall on their face in the presence of errors. The first function we're going to look at is a to I, and if you only think about the success case of parsing an integer, if you only think about strings that actually represent integers, the signature of this function is perfect. It takes in a string and returns an integer. But if we pull out some type theory, and we think about the cardinality of the string type and the cardinality of the integer type, there's a ridiculous mismatch. There are far more strings than integers. And this suggests to us mathematically that there are some strings that don't represent integers. And if you've ever written a book, you know this to be trivially true because your entire book isn't just a string of numbers. But A to I doesn't have a pathway for this. Integers almost definitionally don't have a not an integer representation. And indeed, what A to I decides to do is in this case to just return 0. But a string can represent 0. It can just contain one character that's 0. And so now our error case aliases a valid case. Context the function had to have synthesized internally is wantonly discarded. And we have no way to figure out what happened. And reading the documentation for A to I even more thoroughly, it gets more concerning. Because A to I just blithely skips leading white space, and if it runs into an end of a string of numbers, it just decides that's not a problem. And so if you feed A to I the string 4 spaces followed by the number 5, and then the word foxes, it says, well, that's just a valid representation of 5. But let's imagine we want to save A to I. So we put on our MySQL developer hats and we write a function called real A to I, one that wraps the return value in an optional so we have a not an integer representation. We go off and we call A to I, and if it returns something truthy, if it doesn't return 0, we just return that. Great. We parse an integer. We imagine for the moment we're fine with leading white space, and we're fine with trailing non-numeric parts. But what happens now? Does this 0 represent an error? Or does it actually represent 0? And so what I do in the last half of this function is I write a rudimentary string parser that tries to figure out if a string is an integer representing 0. But that raises a philosophical question. What is the point of A to I? The point of A to I is to parse integers. It's to abstract that problem away so we don't have to implement it. But if I want to use A to I in some manner that approaches correct, I have to write an integer parser. And so I'm going to go ahead and posit that because of these deficiencies in error reporting, A to I is unsuited for any use. So let's talk about stir to L. Stir to L is an upgrade of A to I, no doubt. It has more parameters, and one of them gives us a channel to pass additional context back from the function. The char double star stir end. Ignoring for the moment that it's woefully const incorrect, it is star stir end is set to stir on error. So from outside, we can observe whether or not the string that was parsed was actually an integer. But this raises another question, because is not an integer really the only signal we want from this function? Is it really the only context that it synthesizes and becomes aware of in the process of parsing an integer? Or does it perhaps know that the error was because the string was fundamentally non-numeric, as opposed to being just too large to be represented in the target type? And stir to L doesn't allow that information to escape. But it does allow information to escape about trailing non-numeric parts. It uses star stir end to report the address of the first non-numeric character. And so if this is an error to us, we can easily diagnose it. But it still just assumes that we don't care about leading whitespace. It gives us no indication that there was leading whitespace in the string, that it parsed 4 spaces and then 5. And so we get to C++17. We get to from chars. And now we actually get a struct returned and the integer is reported through an out value, so we can support any type of integer. And when we look at a putter and an URC in a struct, it gives us hope that we're going to get a lot of context out of this function. That we could even get the context of where the parse failed. Information that stir to L kept from us, because it needed to reserve star stir end equals stir for error. And indeed, we do get through EC the context that we complained about before. We get whether it failed due to an overflow, an invalid argument, or was actually successful. But unfortunately, putter is mandated to be set to first on failure, which means that we don't get any information out about where the parse actually failed. Information the function doubtless synthesized internally. And from chars still skips leading whitespace, which leads us to a refinement of our principle. And that's that we should fail fast and fail often. If we're writing an integer parsing routine, all we need to do is parse integers. If the users want to be able to trim strings on the left because they're dealing with user input, they probably have many different kinds of user input. They should probably be implementing left trim as a standalone function. Us implementing it for them and expanding our responsibilities, increasing the space that needs to be tested of our function, doesn't really help, because left trim is easy to write, and anyone who wants it is probably going to need to write it anyway. But now we've taken a tour through these 3 functions, and the other thing that we've seen is that they report errors in very different ways. They have very different error vocabularies. Arguably, A to I has no error vocabulary and is therefore unsuited to any purpose. Stir to L uses a reserved value of an out param, and from chars is the most C-like. It returns an enumerator that indicates the exact class of failure that occurred. And this is not a bad way of reporting errors. It's not bad to use some integer or enumeration to report a code which indicates the exact kind of failure which occurred. Many C libraries do exactly this, all the way from POSIX to libcurl to MySQL to OpenSSL and many others. But what happens when you want to compose those components? What happens when you want to call out to a POSIX function and a curl function in the same function and report those errors up to your caller with full fidelity? And so we need something that can combine together errors from multiple sources. And so the standard gives us std error code, which not only contains an integer, but also contains a pointer to an error category. Some policy about how that integer should be regarded. And 2 errors that are represented by identical integers are deemed to be non-equal if they have different category pointers, which is a problem that is kind of maligned and is one of the reasons why they want to standardize status code. The idea that every category needs to be a singleton makes you run into all kinds of problems when you go to link. But this idea of having a fan endpoint, having a vocabulary type that can represent any error, provided it's represented by an integer as long as it comes from a category, raises yet another question. Because when we were in the C-style world and we got back an error, we knew exactly what category, morally speaking, it was from. And so if we had some fallback we needed to take, if the error was no such file or directory, and we knew we were dealing with POSIX errors, we could just check for enoent. And if we were dealing with curl errors, we could check for curl E, file couldn't read file. But now we've established a vocabulary type that decouples the caller and callee from knowledge about how they're communicating errors, that makes those integers, in some sense, opaque. And so how can we get this ability back? How can we gain back the ability to diagnose broad classes of failure rather than just identifying specific causes? And since we're computer scientists, the obvious answer is to just add another level of indirection. To add a new type which is structurally identical to SystemError code, containing an int and a category pointer, but which is semantically very different. Whereas SystemError code is designed to represent a very particular cause of failure from a very particular component, SystemError condition instead represents very broad categories of failure. You can imagine an error code whose specific cause of failure is, I could not read the TOML file the user provided on the command line. But the broad class of failure that's a part of is just no such file or directory. And so error conditions and error codes can be compared by way of the equivalent member function of the associated category. This equality allows for several error codes to be identified as being no such file or directory, but perhaps less obviously this goes the other way. It's easy to imagine several realizations of no such file or directory. What's more difficult is to imagine an error code that's a member of two broad classes of error, until you consider that maybe an error is both file not found and IO error. Maybe it represents that a file couldn't be found, but also that there was some fundamental problem of the underlying IO subsystem. So let's take a look at some code. Let's try and implement our own error enumeration that communicates our own specific failure modalities. And so, of course, we define an enumeration with 4 enumerators. Idiomatically, the first represents success and is given the underlying value of 0. This causes an error code containing it to be falsy, to be able to be identified as success. Then we need to write a make error code function, which can be found via ADL, which accepts an enumerator and returns an error code. Internally, we use a function local static to achieve the singleton property that's required of error categories. We give the error category a name, which allows us to identify the subcomponent emitting this failure, and then we provide the message member function. Something else that is not liked about this function and that is trying to be ameliorated in status code is the fact that it exposes std_string in an API and therefore requires you include string and all of the allocator machinery to use your C-like error reporting. But at any rate, we cast the integer back to a member of our enumeration, we switch over them, and we return a human-readable description of that specific cause of failure. Which brings us to default error condition, which takes in one of our specific failure modalities and coalesces it to its broad class of failure. Note that this is only appropriate in the case where a code is a member of one class of failure. Now, all of our non-success enumerators represent invalid argument, and so if the code is truthy, we just return std_erc invalid argument. Otherwise, we return a default constructed error condition, which is implicitly success. Which brings us to those equivalent functions that are used to establish whether or not one of our error codes is a member of a broad class of failure. But these are implemented by default in the base class. And I've just pasted their default implementations to show you that as long as you implement default error condition, and as long as each of your codes is a member of only one broad category of failure, you don't really need to provide these functions. But here they are on the slide in case one day you want to write an error code that's both file not found and IO error. Now that we've written our error category, we wrap up the enumerator cast to an int and a reference to the category in an error code and return it. As a quality of implementation detail, we open namespace std, we specialize isErrorCode enum for our enumeration type, and we derive from true type. What this does is this causes SystemError to be implicitly constructible from enumerators from our enumeration. Which brings us to the last member of this family, which brings us to SystemError, which provides an exception wrapper on top of an error code. You construct it with an error code, and you can now throw it as you would any other exception. An idiom that I like to use in my code is to not just throw system error, but to throw some type which is derived from system error and which provides a custom what function. This allows me to inject a very descriptive string with a lot of context that can't be represented in error code, but also throw a system error. Then whoever's up me on the call stack can catch system error, and if they can handle error codes and want to handle system error, they can access that context. But if they don't want to, and that exception is allowed to propagate all the way up and is caught just as an exception, they can still call what? And not just get no such file or directory, but also apps maybe get the name of the file that couldn't be found. Which raises an interesting point. I've talked for a long time about error handling, and I haven't talked about exceptions. What does our principle tell us about when we should throw exceptions? The common wisdom, of course, is that exceptions should be reserved for exceptional situations. But how do you know a situation is exceptional? Who makes that decision? At what level of analysis? Let's say I'm writing an XML parsing routine. Is invalid input exceptional? What if my user's using my XML parsing routine to heuristically check the file system to see if files are valid XML? With that added context, maybe it's not invalid XML that's exceptional, but rather valid XML. And so for most low-level components, exceptions aren't just unsuitable because they introduce hidden control flow. They're not just unsuitable because they have performance cost. They're also unsuitable because the decision to use an exception indicates a decision about the context in which your low-level component will be used. But that kind of goes beyond responsibility component. And so exceptions become more and more appropriate as you move up through the layers of your application. As you take and you combine more and more and more functionality, the strengths of exceptions, the fact that they allow for you to write essentially branchless looking code, and the fact that they can transport large amounts of heterogeneous context comes into focus simultaneously with the purpose of your application and what is exceptional coming into focus. And so when I write code at the lowest level, I only traffic in error codes and custom ad hoc context. Only as I bring together large pieces of my application for testing do I start throwing exceptions just to make my life a bit easier. But now that we have an error vocabulary, now that we have a guiding principle, let's look at an error message from the real world. Let's say that a client opened a ticket and said, a tag could not be parsed as an integer. What would you do? What would I do? I would probably immediately doubt my code because no one wants to go to a client and put their foot in their mouth by accusing the client of being wrong. And so I might spend the whole afternoon chasing down leads and writing new unit tests and checking for some erroneous emission of this error. And only then would I go back to the client. But what if I kept something from you? What if this isn't actually the whole error message? What if instead the client opened a ticket and said the system emitted this error? Would your response be the same? If you worked in finance and you understood the fix protocol, maybe you would just look at that buffer. You'd look at the caret that points to the exact point of failure, and you'd say that tag doesn't look like an integer. 5a isn't an integer, the tag could not be parsed as an integer, and in 5 minutes you'd reply to the client's ticket, and you'd say, well, one of your peers is sending you invalid fix messages. You get your whole afternoon back. And so how can we write code that allows us to emit this kind of error message? How can we write a fix message reader? Well, to write a fix message reader, we need some way to get out fix messages, and so we have a next function that returns a non-owning pointer to a fix message and takes in an error code as an out parameter. This is a much maligned idiom that may one day vanish when we get stood expected, but for now it's idiomatic to return a value and pass in an error code as an out parameter, clear it on success, and set it to some error code on failure. But that still just gets us tag could not be parsed as an integer. And so maybe we add another function. Maybe we add a way to ask the fix message reader to format its last error as a string. We give it an opportunity to emit some free-form context, and that gets us the error on the preceding slide. But we're making some assumptions about how our user wants to use this component, aren't we? What if our user doesn't want to just format the last error? What if they have some programmatic way of remediating the last error and they want to examine the context thereof? Or what if the user just doesn't like our error message format? Why is format last error privileged as a member, poking around in private data and using it to format one particular realization of the context generated by the parse. And so we fix this. We fix this by just adding getters so that we can get the state left over by the last parse. We take our format last error function, and instead of making it the ground source of truth about failures, we just make it a convenience function. We imagine most of our clients will want an easy turnkey way to format their last error, and so we give them one. But we don't access any private data from inside there. We go through the public interface. And so if our clients decide that they don't want error messages or they want a different format, they can get it. But a fixed connection does way more than just parse fixed messages. It has a socket it needs to maintain, some timers. It has a fixed log. There's a lot of different components there. So how can we keep error context moving upward through the stack? How can we propagate error context through a fixed client? Obviously, we can provide a stood string getter that returns a formatted error, but now we're back running afoul of our principle again. We're making assumptions about our user's use case. And so what we need to do is we need to give the user some way to establish which particular subcomponent generated the last failure. We need to provide them some way to be able to go through the subcomponents, decide which errors they care and don't care about, and maybe implement format last error for themselves. And so we do exactly that. We have an enumeration of sources of the last error. We allow the user to retrieve it, and then we give them getters for subcomponents. So if they see the last failure was a parse failure, they can grab the fixed message reader and they can inspect it to decide what they want to do next. Which brings us pretty close to the highest level of our application. We've parsed integers, we've written a fixed message reader, and now we've brought it all together with a fixed connection. But as we approach the highest level of an application, we run into a problem. And that problem is multi-threading. Because previously we were discussing things in the context of a call-er, call-e relationship. We assumed there was some way to transmit information back up the stack about the errors that occurred. But when you're in a stood thread, there's no one above you on the call stack. If you return, the thread just ends and the rest of your system goes off running happily. And I'm sure that's a failure modality that a lot of people have seen when errors are generated in multi-threaded programs. No, instead you need some way to coordinate threads, to coordinate work, to detect errors, to fan those errors in, to shut the threads down, and only then re-emit the failure. And for this reason, along with other reasons, I like to say something about multi-threaded programs, and that's that they're easy to get started, but they're really hard to stop. So let's take a look at a component that can manage a pool of threads. Let's write a thread pool. It has a state, and we've decided we're going to use IO context from ASIO to manage the work queue. That's not really what we're concerned about anyway. We're concerned about that high-level error handling. And each state has a thread, the worker thread that's servicing it. And internally, we keep a list of these states, and we have a mutex, and we have an exception putter to fan in the error. And then we have a constructor that determines the number of threads, and we can call run, surrender the foreground thread in a blocking way, and run all of the execution context by spinning up some background threads. Then we have a stop function that we can call both nullery and unary. If we call it nullery, it just asks the thread pool to shut down gracefully, to stop all of the workers and surrender control back to us from run. But if we pass in an exception putter, it actually becomes a way for us to integrate external components. If we have an external component that encounters some failure, we can call stop with that failure, and that will cause the thread pool to collapse, re-emit that failure, and serve as a fan-in point for our entire application. Then, since we want to be able to actually distribute work to this thing, we have a begin and an end iterator across the states, so we can do that. But just looking at an interface doesn't really help you write code that's complicated. It doesn't help you solve all of the sharp edges involved in spinning up some threads and then fanning them back in correctly without leaking anything or leaving it on the floor. So let's actually write that run function. The first thing we're going to do to help ourselves along is we're going to write a lambda, run, which takes in an execution context and tries to run it. And if running it fails by throwing an exception, we ask the rest of the thread pool to stop. We give them the exception that we emitted, we cause them to fan in all the other threads and emit that exception. Then we enter an anonymous scope, we grab an iterator to our first state, and we bump it by 1. And the reason we bump it by 1 is because the foreground thread is going to be surrendered. It's going to run that first context, and so we don't need to make a worker thread for it. Then we go off and we create an anonymous scope guard. We create an anonymous scope guard to work around the fact that thread creation can actually fail. Thread creation being one of these operations that a lot of people think of as always succeeding, but which can actually fail. You can create 2 worker threads and then try and create a third, and an exception gets thrown. And if you're not careful, control will leave your function, and 2 worker threads are running, and some others aren't, and who knows what that's going to run off and do to the state of your application. And so inside of our scope guard, we grab the first iterator and bump it by 1 again. And then we loop only up to the point to which we've created threads. Because we don't want to deal with the thread that failed to be created, we loop up and we stop exactly where the outer loop got to. For each thread we visit, we ask its execution context to stop. We join the thread to make sure it's not off mucking with program state when we don't think it is, and we fall off the end of the destructor, thereby ensuring that no matter how we leave this anonymous scope we've introduced, all of the threads will be fanned in and ended. Then we just continue looping across our states. We spawn threads, and we pass them a lambda, which just calls our run function. Note that we're very careful to capture the begin iterator by value, because the last thing we want to do is introduce a race between the thread and the loop that is spawning the threads. Then, of course, we turn to the foreground thread, we ask it to run the first context, and everything goes off and runs. Once control leaves all of those run functions, once we run the destructor, when we hit that all-powerful closing curly brace, all of the threads have been spun down. They've all stopped, and we've gathered the error context from the first one that failed through our stop member function. All that leaves for us to do is acquire a lock, examine the exception putter, and if it's truthy, we re-emit that failure. We teleported it from whichever thread experienced the failure back to the one which was below main. We threw it, and now our user can catch it and write it out to their user in turn. Which is the highest level of the application, right? We finally brought everything together. We finally fanned in and managed all of the error context. But let's think about another error. Let me show you another error that I've seen actually at work. One that recently caused consternation. I wrote a network server. It emits log messages like this when the connection experiences some failure. This one failed because it couldn't read from the socket because the socket was at the end of the file. A client had an issue with this system, and a member of the operations team went off and was going through logs trying to sort out what was wrong. And saw all these failures and came to me and said, "It says here there's a failure. Is this actually a problem?" And I, having written many network programs, was like, no, the connection just reached the end and we shut it down, we reaped it, it's fine. Client connections go away. And so the member of the operations team was able to go off and actually sort out the client issue. But when I was preparing this talk, I thought about this failure. Because this really raises an important question in error handling and reporting. And that is, whose error? An error to who? Because in our previous situation, read, the low-level system call, does not regard end of file as an error. It clears errno, and it returns 0, and it reads no bytes. That's perfectly acceptable. But at a higher level of analysis, let's say we want to write a component that deals with partial reads, and so we want to request exactly 16 bytes be read. At that level of analysis, all of a sudden reading 3 bytes and running into end of file is a big problem. That success case to read is now an error to your operation. But then as we reach the highest levels of analysis, if we reach the layer of the server where it's coordinating all the client connections, it doesn't really care that the connection reached end of file. It's just going to tear it down, reap it, and accept all the other connections that come in. Which brings us to a situation where succeed, fail, do we really care? At the highest level of a TCP server, if a connection from a client fails, does it matter? What would it mean for that to succeed? What does it mean if your TCP connection gets to the end of its run and it succeeded? Does that mean that the connection wasn't reset? That you didn't reach end of file? How can that actually happen? And so at some level of analysis, we need to reach a point where we have sufficient context to look at failures, to look at errors, and say, this doesn't really matter. This only matters to the subcomponent that emitted it. It doesn't matter to my broader system. Or we need to check it and see if it's part of a specific failure modality, and then make that decision. But the thread pool that we just wrote, that we were going to use to manage all of the work at the highest level of our application, it deems every single failure to be utterly terminal and critical. If any piece of work throws an exception and that exception is caught, it immediately shuts the whole thread pool down. There's no seam for us to inject intelligence about which errors actually matter to us. There's no way for us to keep the system running when we want to ignore a failure. Which means we need to take a different approach. So let's take a look at a piece of code that my company uses. Let's take a look at a processor manager. The purpose of this processor manager is to coordinate devices which are receiving raw packets and feeds which are processing those, parsing them, and emitting market data messages downstream. To do this, it spins up some background worker threads as dictated by the processor manager settings, which aren't relevant to this presentation. We have a start function which starts the background threads, and we have a stop function which fans them in and shuts them down. But that's not really a lot of information to go by. We call start and the background threads are running, but are they still running? Have they failed? Is all of the work done? When should I call stop? And so we inject a callback. We inject some user customizable component which can receive events emitted by the system and then reach back into the processor manager and according to its own rules. The processor manager callback looks like this. It has 4 events for device processor and packet processor begin and end, with a device processor thread being one that reads packets and a packet processor thread being one that actually provides a context to process them. Our begin and end events both actually have a reference to the particular subcomponent which is generating the event. We give the user that context so they can decide how to handle things. But that's not all the context we have available, because when those threads reach their end, there's going to be some reason they reach the end. Maybe it's success, maybe it's failure, but that thread will have that context available. And so we provide a pathway for passing that through as the threads end. We give all the context to the user, and then we allow the user to implement only their concerns. They implement only their logic around when the processor manager should start and stop, which failures should be good and properly terminal. That allows us to write something that looks like this, something that I actually wrote recently for a project, a processor manager callback designed to handle end-of-file specifically. Because while some devices go off and read from NICs, which is a theoretically unbounded stream of incoming packets, some devices actually are backed by PCAP files. And PCAP files are very well delineated. They have an actual end. And when they reach an end and you try and read a packet from them, you get an end-of-file error. It causes their associated device thread to end in error. And so inside this processor manager callback realization, inside the event handling, I check for end-of-file. And if end-of-file is the error, rather than shutting the whole processor manager down and causing the application to fail, instead, I wait for all of the other device processors to also end with end-of-file. And then when the last of those ends in end-of-file, I go off to each of the packet processors and I wait for it to flush its queue. And then once I'm sure that all of the market data has been processed downstream, only then do I allow the run to end. And to answer the questions about start and stop and how do we know when we're done, I have a wait member function that the person who started the processor manager can call, which will block the foreground thread until the processor manager run is finished according to the definition that I've injected, where end-of-file causes a successful end and errors cause an unsuccessful end. Then, once they've returned from wait, they can go off and they can ask me if I ended due to end-of-file. And if I return true, they can be happy and the application can succeed. Otherwise, they call maybe throw. They go into the callback and they scrape out all of the context that I save and they throw it as an exception. It gets fanned in from whichever thread generated it, saved, rethrown, caught in main, and finally logged to the user. Which brings us to the 2 stragglers in this formulation. Which brings us to warnings and logging. 2 things that trigger people into this kind of special pleading, where they give the principles of software engineering a runaround. I don't have a channel for warnings, and so I'm just going to dump them to the standard output stream. But the problem with that is that even more so than errors, the idea of a warning contains embedded in it the idea that you need context to decide how to handle it. Because if it was always a failure, it would just be an error. The fact that you've deemed that it's a warning means that you know it's not an issue to some callers. And by reaching out to global state and just writing to standard out, what you've done is you've told those callers that you always think that's worth showing to their users. You've made it very difficult for them to embed your component in their component cleanly. You've widened the responsibilities of your component unnecessarily, and in so doing, you've reduced the number of circumstances in which it can be used. And so even if it's difficult, even if it involves restructuring code, warnings need a proper channel. And the same kind of analysis applies to logging. People love to use logging as the runaround on the prescription against global state. I need a global logger. But what if your user doesn't want any logging output? What if your user doesn't want certain classes of things to be logged? What if your user wants two different components to log in two different ways? And you may try and give this the runaround and say, okay, well, I'll inject a logger. But again, what if the user doesn't like all the things you log? What if the user doesn't like your logging format? What if the user wanted to react to those events by not even logging at all? Because what your component was actually doing when it was writing to the log wasn't writing to the log. That was just something you did, expanding your responsibilities to fulfill a particular use case. Your component was emitting events. And so you need to reify those in something that can handle events, an observer. And then you expose your client to the fullest context that your subcomponent generates. Not only that, but if you want to be truly nice, you can go off and you can implement a realization of that interface that just does the logging you want it to do anyway. You can have your cake and you can eat it too. So as you leave this talk, what should your takeaways be? Well, the first one is to not assume that std_threads constructor doesn't throw. To not assume that that will never happen. Integers can overflow, std_threads constructor can throw, and malloc can return null. Don't throw away potentially useful context. Don't assume that because you carefully and painstakingly synthesized information, that some failure makes it totally irrelevant to your user. And remember that guiding principle, to not make assumptions on behalf of your user, to not broaden the responsibilities of your components and thereby limit the use cases to which they appertain. Because maybe if you follow these principles, one day it'll be the difference between this error message and your phone ringing at 2 a.m. And this one, and the operations team being able to do their job and let you sleep. Are there any questions?
A lot of what you suggested sort of hinges around the idea of being able to pass a context through things pretty cleanly. Do you have suggestions for how to get there from a system that doesn't already have that?
So the question, I was asked to repeat questions. The question was about, a lot of the stuff I talked about assumes that we can transmit context. What would I do in systems that don't have the ability to transmit that context? And so what I would say, there's a couple different scenarios that I found myself in that situation. So there's one where there's like good and truly no path through. And in that case, you're either stuck with breaking the rules on either side because the person you're going through broke the rules, or you're stuck with trying to create back channels, right? Like, so, they might allow you to pass through a void star and you might use that. That's the lowest hanging fruit. On the other side, there may be some way for you to ferret information away in like something that approaches a global, like a thread local or an actual global, and then you use that in a very tightly defined subsystem that interacts only with that component. That's something that I've done quite a bit. You have this badly behaved piece of code, but you really need to use it. And so you write a lot of badly behaved code around it, and then you seal it off, right? Like, so for example, in the logging example, I work with a lot of code that just goes off and globally writes to the log. And I had a piece of code I wrote once that wanted to walk over like a bunch of different feeds. And if it couldn't initialize them, it was like, that's fine. I just don't run that feed. But this just spat hundreds of lines of error logs out to the log for no reason. And so what I had to do was I had to write a component that went into the global logger and disabled it for a bit, and then re-enabled it. And then I sealed that in something that I could test and build confidence in, and then I could build the rest of my software properly. And I think that's a fairly standard approach to take when you're interoperating with a legacy system that's just not well behaved. You need to either give it a runaround, or you need to break your own rules and try and just constrain where you're breaking the rules. Because too often people are like, oh, I need to break the rules here, I got to break them everywhere. So I hope that's an answer to the question. There's a question from online.
There's a question. Stood expected was briefly mentioned at the beginning of the talk. How does this approach to error handling change with the inclusion of such a library? There's also TL expected, which is widely used.
Yeah, so the question is about expected, and I briefly mentioned it. I think it just helps us do away with that idiom that people don't like, where you pass in the error code as an out parameter. And the reason people don't like that is because it requires the thing you return to have some reserved value that you can return even in success cases. For pointers, it's obviously null, and for integers, it's obviously 0. But when you get to more complicated code, the idea that you need to return something to report your error through an out parameter is not good. And expected just solves that problem by eliminating that entire idiom. So you had a question in the front.
I have a comment. Maybe you can comment on my comment. For the error, usually we want to find out the source of error. So we used to build a logging logic. will print out the thread ID and the file name and the line number. So that kind of like a episodic logging, it will keep like a log some status of the program. And when there is an error, it also logs the thread ID, the file name, and the line number. So that helps us to really find out where the problem is. Then we can get to that file and see what's going wrong. Yeah, how you comment?
Yeah, so the comment about that was that in a lot of instances you want to kind of get a trace of where the program went, and then when you have a failure, you have like a lot of information, not just about where the failure occurred, but what led up to it.
Yes.
That's accurate. So one thing that you can usually do, I mean, you can do that, right? Like you could have some context you pass around that records what's happening, right? Like you inject it and it writes down where it's been. That's one approach. The other approach that I've found, and that actually leads to this error message comes from something that captures a lot of context for what's happening, is that if you can identify with the high-level context that I've talked about through the whole talk, if you can identify the critical moments where like there's going to be a failure and there's some opportunity to omit information about it, then you can fan out from that in your analysis of all the components you're building that lead into that, and you can make sure they give you back enough information, right? So for example, this error message is emitted in response to a client query that fails, right? And so you can see that whatever S3 component we have in the back end has reported its error, and it gets logged out with the domain, the name of the category. But other things like the identifier of the file in the database that was being acted on are reported. And from a very high level, it's not obvious how that context could be captured because the database is very well abstracted. But when I was writing that component or thinking about that component, I thought to myself, well, knowing what part of the database was being acted on is very, very important in that instance. And so when I was designing the database interop component that abstracts the whole database away to like init run, it has this getter to get out the last identifier, right? To make sure that information can be written down. And then I leverage source location to get the file in the line. So to generate this error message, I call a function that takes a source location. And then if, everything else fails and I actually want to understand where in the code it came from, I can at least go to that source location. But if you wanted like a stack trace, you'd be left getting a backtrace, which involves operating system specific magic and compiler flags, or you could pass around a context that you can append things to, right? Like you can say, oh, I was here, I was here, I was here. And then eventually you can either dump that or not.
So this whole context is written by a function call.
Yes.
Whenever.
Yes. In the back.
There will be STP stack trace in C++ 23, and I also expect.
So the comment is that we'll get stack trace, which addresses what I was just saying. And also we expect to get expected. I think the pun might have been intended. Okay, in 23. So that'll help. I mean, I've written code with expected and I really like it. It just has never gotten standardized, and so I end up using the standard idioms. Yeah, so yeah, the comment is it's in the last steps. So there's a question in the back.
I like where you were going with pushing whether or not something is an error or a disappointment to the caller. But even having the option to capture context around or forward errors in the case where an error is a termination as overhead in the success path, or capturing context in the case of something like A to Y about where you failed an error might also add overhead. But adding that amount of customizability into your default return type can be a lot. So where do you go from there? That itself is a decision to capture this amount of context.
Right, so the comment is about the fact that propagating and capturing context also has a cost, and that cost can be borne by the success path as well as the disappointment or failure path. The way that I tend to work around that is that, so in that case, right, like what I think that might be an argument for is an expansion of the responsibility of a component. Right? Like let's say that I want to write an integer parser, but I want to marry into it the idea that transmitting information about where the failure occurred is a non-starter because I'm using SIMD instructions, for example. And so then you write that, but you'd have full awareness of that fact. It wouldn't just be a general purpose utility that falls on its face for no reason, like A to I is. And I've done that in code. Like there's error context you throw away because you actually know from the embedding it's never needed, and if you were to preserve it, you'd end up allocating a string, and I don't want to allocate a string every time I build up some context because I want to be sparse with my allocations. What I'm more getting at is in a lot of instances, writing down the context is really cheap, right? Especially making it available programmatically. It might be a few pointers. It might just be allowing your user to inject the storage you use and leaving that behind. Like rather than me newing up a string buffer and writing my path in that and then throwing it away when open fails, it's like you give me a path, I fill it, I try and open it. If that fails, you still have the buffer and you can totally throw that away. So, are there any other questions? Okay, that looks like it. Thank you very much.